All right, let's just jump right in. Think for a second about the last time you weighed something. Some flour for a recipe, maybe a package you're about to mail. It seems like the most simple, straightforward measurement in the world, doesn't it? You put an object on a scale, a number pops up, that's it. But what if I told you that simple little number is actually the end result of an intense battle against invisible forces, all governed by some pretty deep physics?
Yeah, because that simple act of measurement we all do without a second thought, it's really just the tip of the iceberg. So today, we're going to go way below the surface and explore the incredible hidden science that's required to get a truly accurate weight.
So that really begs the question, right? When you see that number on the display, what does it actually represent? How much can you really truly trust it? Well, as we're about to find out, the answer depends on a whole lot more than you might think.
To really get a handle on what's at stake here, let's look at this tale of two scales. Over on one side, you've got your trusty kitchen scale. It's awesome for measuring out flour in grams, and it's probably accurate within a few grams either way, which is totally fine for baking cookies. But then, you have the analytical balance, the kind you'd find in a high-tech lab. This thing measures in milligrams, or even less, and its tolerance for error is so small it's like trying to weigh a tiny fraction of a single grain of sand. For instruments like these, even the slightest mistake can be a total disaster.
So what is it that causes these tiny, disastrous errors? Well, to get that hyper-precise measurement, scientists are basically in a constant fight against a whole team of invisible enemies in the environment. Let's meet the main villains, shall we?
First up, we have an enemy we've all felt, but probably never ever considered when weighing something: heat. Yep, just the difference in temperature between the object you're weighing and the air in the room can completely throw off your measurement.
Okay, so here's how it works. A warmer object heats up the air right around it. And what does hot air do? It rises. This creates this gentle, upward-flowing air current called convection. It's literally the same thing as that heat haze you see shimmering off a hot road in the summer. And that tiny current is strong enough to physically lift the sample ever so slightly, making the scales show a weight that's actually lighter than reality. And as the sample cools down, you can watch the weight just slowly creep up, making the reading completely unstable.
So how in the world do you fight back against this invisible lift? Well, scientists have a pretty solid game plan. First, they acclimatize. They just let the sample sit out in the room for a while until it's the exact same temperature as the air. Second, and this is crucial, hands off. Your own body heat is more than enough to mess things up, so they always use tweezers. And finally, they control the whole environment, making sure the balance is nowhere near a drafty window or in a beam of direct sunlight.
All right, on to our next invisible enemy. This one messes with the very force we're trying to measure in the first place, gravity. I'm talking about the tilt.
See, a scale is built to do one thing: measure the force of gravity pulling an object straight down. But if that balance is sitting on even a tiny, almost imperceptible slope, the force of gravity gets split. Part of it pulls straight down, but another part pulls sideways, along the slope. The problem is, the scale can only see that vertical, straight down part, and that means it will always report a weight that's lower than the real value.
Now, thankfully, beating the tilt is actually pretty straightforward. These high-precision balances have these little adjustable feet and a bubble level, just like the ones construction workers use, to make absolutely sure they're perfectly horizontal. And hey, if for some reason you just can't get it level, you can actually calibrate the machine right there in its tilted position, basically teaching it how to correct for that angle. Pretty cool.
And now for our final enemy. And this one might be the most mysterious and, honestly, the most frustrating of them all: static electricity. Yep, that exact same force that makes a balloon stick to your hair after you rub it can cause absolute chaos inside one of these hypersensitive instruments.
Just look at what's happening here. If your sample, and this is especially true for things made of plastic or glass, is carrying a static charge, it basically acts like an invisible magnet. It can either attract or repel the weighing pan and even the walls of the balance chamber itself, physically pushing or pulling on the measurement mechanism. This is what causes those numbers on the display to just drift and dance all over the place, making it completely impossible to get a stable, accurate reading.
Defeating static? That requires some serious gear. Labs will often use these special devices called ionizers, which shoot out ions that neutralize any static charges in the air. They can also just put the sample inside a metal container, which shields it, or use special anti-static sprays. Or, and this is a cool trick, they can just raise the humidity in the room, because moist air helps static charges dissipate naturally.
Okay, so we've gone to war with the enemies in the environment. But here's the thing. Even in a perfectly controlled room, the balance itself has its own limits.
To really get what accuracy means, we have to look at the anatomy of the instrument.
First on the list is something called repeatability. Now here's a wild thought. If you weigh the exact same object 10 times in a row, even on the best balance in the world, you're going to get slightly different numbers every single time. Repeatability is the measure of that natural variation. It's not about being right, it's about being consistent.
This classic bell curve shows you exactly how it works. Most of your measurements are going to clump together right around the average value. For a really high-quality balance, the manufacturer basically guarantees that 95% of all your measurements will fall within a super tight range of that average, what a statistician would call 2 standard deviations. The tighter and narrower that bell curve is, the more repeatable and therefore the more reliable the balance is.
All right, let's move on to our next big concept, linearity. This is all about a simple question. Is the scale just as accurate when it's weighing something really light as it is when it's weighing something really heavy, close to its maximum capacity? You want the scale's response to be a perfectly straight, predictable line across its whole range.
On the left here, you can see a graph from a balance that has linearity arrows. See how the line is curved instead of straight? That means it might be dead-on accurate at 500 grams, but way off at 2,000 grams. So what they do is calibrate it. And that process, which you see on the right, essentially teaches the balance about its own quirky curve and digitally corrects for it, turning it into a perfectly straight and therefore perfectly accurate line.
And this brings us right back full circle to our old friend, enemy number one, heat. Sensitivity drift is just a fancy term for how much a balance's reading changes when the room temperature itself goes up or down. Because the delicate components inside the scale literally expand and contract with the temperature, and that can throw off its accuracy.
So when you see a technical spec like plus or minus 2 parts per million per degree Celsius, what does that actually mean in the real world? Well, this slide breaks it down. If you've got a 2,000 gram weight on the scale and the room heats up by 10 degrees Celsius, that tiny little ppm value means your reading could be off by as much as 0.04 grams. Now that might sound like nothing, but in a high-stakes pharmaceutical lab, that's a massive error. So, okay, we have wrestled with heat and tilt and static. We've talked about repeatability and linearity, and you might be sitting there thinking, wow, why on earth would anyone go to all this trouble? Why does this insane level of precision matter so much?
Well, it matters in fields like pharmaceuticals, where the active ingredient in a single pill might only be a few milligrams. That tiny error caused by a bit of static isn't just a number on a screen. It's the difference between a medicine that works and one that's dangerous. In material science, it's the difference between a revolutionary new alloy and a catastrophic structural failure. These invisible, microscopic details have very, very visible, real-world consequences.
And all of this really leaves us with one final big thought to chew on. We've just peeked into the universe of complexity hidden inside one of the simplest things we do. So it really makes you wonder, doesn't it? If just weighing something is this intricate, what other everyday measurements, telling time, measuring distance, what other things do we totally take for granted? What other invisible forces are out there quietly shaping the numbers that shape our entire world?